So here we'll be looking at some probability axioms and properties that we can use to prove other more complex probability statements. The first three of them here are known as the probability axioms. They can be used to prove just about everything else. And what we have here is that the probability of A is between 0 and 1. The probability of any event is between 0 and 1. We should know that. The probability of the universal set, the probability of everything happening, is 1. That's something's going to happen. Either A is going to happen or not A is going to happen. And then the third one says that if two sets are disjoint, that is, if A intersect B is what we call the empty set, if there is no intersection, then the probability of A union B is equal to the probability of A plus the probability of B. And then we have three other probability statements down here. These are properties of probability, and we're going to prove the fourth one using the first three axioms. So here we go. Get ready for this fun. So we know that we could say the probability of A is equal to the probability of A union the empty set. Because if we take the union of any set with something that has nothing in it, we still have that set we started with. It's the equivalent of adding 0 in our number system. And since set A and the empty set don't have anything in common, that is, we have this condition being satisfied right here, A intersect B is the empty set, we can apply axiom number 3 and say that our probability of A is now equal to the probability of A plus the probability of the empty set. And if we simply subtract the probability of A from both sides, we get that 0 is the probability of the empty set. There we go. There's our fourth property in that list. Now we're going to prove the fifth one. We're going to prove that the probability of the complement of A is 1 minus the probability of event A. Another way to read complement of A is the probability of not A occurring. So we're going to start with axiom 2 here. We're going to start with the probability of the universal set. That can be thought of as being the probability that event A happens union with A not happening. Because A either happens or it doesn't. Those are the two possible outcomes that we could have. And we know from axiom number 2 that the probability of universal set happening is 1. And we also know that A and its complement are disjoint. That is, their intersection is the empty set. There is nothing in that intersection. So the probability of A plus the probability of not A. So simply subtracting probability of A from both sides, once again, we now have the probability of the complement of A is equal to 1 minus probability of A, which is what we were trying to prove. So two short proofs using these axioms, and we're going to look at one that's a little bit more complicated in the next example, and we'll use multiple of these properties, not just the axioms. So here we go. We want to prove that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. This is a well-known probability fact. And it's something that we used in the previous sections that we took notes on. I mentioned it. But I want to prove it now. Not just assume that it's true, but prove that it's true for all events A and B. And there's two things that can happen. Case 1 is that A intersect B is the empty set. So this right-hand side we can rewrite as the following. Probability of the empty set is what we're subtracting, and we know from our axioms that the probability of the empty set is 0, so the probability of A union B equals the probability of A plus the probability of B, and that was axiom number 3 that we had. So that we know. Now let's look at case 2 for this proof. Case 2 is that A intersect B is not the empty set. Okay, so how do we deal with this? Well, if I draw a Venn diagram, it can help me to visualize what's happening. So here's A, here's B. A union B, that is everything in both of them, could be thought of as A union B, but with A intersect B removed. This means take set B and remove the intersection A intersect B. So that's just referring to this part. So A union B, all of this is all of A plus that little nugget out there. So the probability of A union B will be the probability of this thing. A union B removing A intersect B. Now, what can we do here? Well, these two sets, A and that part, they're disjoint, which means we can use, since these two things are disjoint, if I go back to my list, we can use axiom number 3 to split this probability into two parts. So this is equal to the probability of A plus the probability of B with A intersect B removed. And from the sixth property, we know that this part can be expanded into probability of B minus probability of A intersect B, and that's what I was trying to prove for this. So there's our proof. This one we had to consider two different cases. This is a brief introduction to a little area of mathematics called group theory. We are fairly simplistic with it. One thing that I did leave off, the whole reason we can do this part is because A intersect B, if you look at this property, it says that this part must be a subset of the first one. And if we look at this picture, A intersect B, this part in here, that is a subset. It's a smaller part of the big set B. So there we go. This is where we stop. And you're going to get a chance to do some of these proofs yourself in your practice problems.